Hello everyone, and thank you so much for tuning into this video. My name is Gregor Doehner. I'm a PhD student at the Technical University of Munich in the Thermo-Fluid Dynamics group. And this video is a recording of a talk that I gave in early April 2025 at the Euromech Colloquium on data-driven fluid dynamics in London. The topic of my talk was data-driven modeling of the flame response using universal differential equations. Well, and with that out of the way, I suggest we jump right into the video. All right, so the premise of this talk is that we want to understand flame dynamics since those dynamics are crucial for predicting the onset of combustion instabilities. Now, combustion instabilities are a phenomena where the flame goes into a feedback cycle via the acoustics of a given system, leading to growing amplitudes in pressure, heat release rate, velocity fluctuations, overall putting a lot of strain on our system. It can ultimately lead even to the destruction of the combustion system, and we really want to avoid them, and for that we need to understand the flame dynamics. Now, flame dynamics comprise very rich dynamic behavior, including saturation and harmonic effects. Okay, so how can we now model the flame response? First of all, let us define some model interfaces. So as input, we define velocity perturbations, which are defined as here given on the left. So we have the instantaneous value of velocity u of t, and we subtract from that the mean of the velocity and divide by the mean. The output is obtained in the same way, just that we apply it to heat release rate fluctuations of the flame. Here you can see how such signals typically look like, and this is also our training set. Now, this yields now a general flame response model where we say q dot prime of t, so current heat release rate fluctuations, are a function of current input velocity perturbations and also x of f, something that we call an internal flame state. So this is just there to emphasize that the flame is a very dynamical system, and as such a dynamical system, its next output will not only depend on the current input, but also on the history of the system. So if you imagine, for example, a car, your next movement will not only depend on the position of your accelerator or the brake input that you give, but also on the velocity that you have and the acceleration that you have right now. And this is what we try to emphasize here. The flame is a very dynamical system. And for such a dynamical system, a common approach, if we go to the machine learning world, would be to use something like a long short-term memory, a neural network, or maybe an echo state network. However, those systems, as potent as they may be, they don't really provide an input into the underlying dynamics of the system, and it makes it very hard to understand what is actually going on here. And for that, we may want to try a different modeling approach. So we want to use an ODE, so an ordinary differential equation, which is inherently used to describe dynamical systems. So first of all, we need an ansatz for this ODE, and we claim that we can understand the flame sheet as a collection of local elements, and this basically yields the ansatz for the ODE formulation. So if we have a look at this figure here on the left, we can see the global flame sheet. And we can now say, okay, we have a look at this on a local level. And here we see this continuous flame sheet as a collection of local elements. Each local element can be displaced by flow perturbations or by the position of adjacent elements. So if the element to the left of our current element, so this one here, is displaced, this will also lead to the displacement of the next element downstream, just because the global flame sheet is a continuous phenomenon. However, once we are displaced, we as a local element, we also experience a restoration force. So this is kind of comparable to a spring. This restoration, however, is not instantaneous, so this is all associated with some inertia and some damping. When I use those terms like spring, inertia, damping, it becomes pretty obvious that we are talking about a somehow coupled system of oscillators. In previous work, it was shown that for the flame at hand, which is a simple laminar slit flame, a 2-mass spring damper system suffices to adequately model the present flame. So we obtain a dynamic ordinary differential equation, as given here on the left, and The input is represented as a force on the first mass. So you can see a visual representation of this ODE here on the bottom right. The output Q dot prime of D is represented by the position of the second element. And we apply a delay to the output to match the delay that we observe from input to output in the true flame. So this is all the parameters that you see, this alpha, this epsilon, the delay, this all can be calibrated on broadband time series, so on the data set that I just showed earlier. And after tuning all the parameters, we obtain a system or a dynamic model as given here on the top right in terms of impulse response, which can reproduce flame dynamics very accurately. So, however, I mentioned that flame dynamics are very rich and also very nonlinear. So they also contain something like saturation. And saturation effects are a nonlinear phenomena. So we need something nonlinear in our ODE. And this nonlinear thing is basically the cubic damping term that you can see here in blue. This cubic damping term suffices to induce saturation, which closely mimics what we observe in real flames. So we are now able to recover not only the flame transfer function, so the linear response of the flame, but also the flame describing function with high accuracy, so the FDF is recovered. Saturation, or to obtain saturation, is a nice thing, but there's more to the flame response. And when I say more, I want to put a special emphasis on the harmonics that we can observe in a flame. What do I mean by that? So consider that we force our flame with 100 Hertz, so a harmonic signal, at an amplitude of 0.5 or 50% perturbation amplitude. Now, black dashed in this figure represents the true response of the flame. And you can see that the response is very, very nonlinear. So the response is not only happening at the fundamental frequency, so at the frequency at which we force at 100 Hertz, but we also have higher harmonics. So at 200 Hertz, 300 Hertz, 400 Hertz, up to 1000 Hertz, the flame responds with varying strength. This leads to this overall very nonlinear looking signal that we see in black. Our calibrated model, however, does only or majorly respond in the fundamental frequency, so in the frequency at which it is forced. Therefore, our current model, our current ODE, lacks harmonics. So what can we do now? In such a case where we already know some part of the physics, or we can approximately describe our problem with some given ODE, such as here in the first equation, universal differential equations, or in short UDE, provide a very nice framework to extend a given ODE. So the UDE approach is we want to account for unknown dynamics with a universal approximator. So second equation on this slide, we now say we know some parts of the physics, so we know the x of dt is at least f of u and x. So in this case, this would be flame dynamics is at least to some extent described by our oscillator system, but we are missing something, and that something will be approximated now by our neural network. This UDE is now again trained on broadband time series data. So again, how can we imagine all of that? Now we see again what we had before. Everything in black is just the default ODE that we already know, for which we know that the FDF is recovered nicely. And now in blue, we see an additional term, which now transforms this ODE into the UDE. So we now see a contribution that is approximated by a neural network. And how can we imagine that? If we look at the elements on the right, so the physical representation of the ODE that we are looking at, we can now see that the neural network is acting like some nonlinear force on the second element, which is approximating what we are currently missing. And after training, we get a quite good looking performance in time domain. So again, calibration of all the weights now of the neural network and also of the parameters of our ODE is happening on time series data. If we now evaluate our new system, our UDE, in terms of harmonic response, we obtain the results presented here. So now in blue, you see, in addition to the already presented results, you see the response of our UDE, so of our system that is now enhanced by a small neural network. And you can immediately observe that the addition of the neural network significantly enhances model performance. So again, in blue, we now see a significantly richer response. So we have harmonics basically also up to 1000 Hertz. matching nicely what we see in the flame. And also the fundamental contribution is predicted significantly better. The shape match in terms of output signal is not perfect, but it is significantly better, significantly more nonlinear, comprises significantly more dynamics than what we observe in the default ODE. Now the problem is, someone might argue, that we've just, well, moved the problem to a different plane of existence. I said earlier that we don't want to use neural networks because they are black box systems, and as such they don't really provide an insight into the physics that are happening. But now we used a neural network. We used it inside the ODE, so a lot of the heavy lifting was already done by the ODE, but still we don't really know what the neural network is doing. Now, in such a situation, PySyndy, or generally symbolic sparse regression, comes in very handily. So what we do here is, we say, well, we train a UDE with broadband time series data. That's what we already did. So we have now a trained system which has a significantly richer harmonic response. Second step is now to excite said UDE with some broadband data, ideally a signal that, well, triggers all the dynamics inside the system, and record the states of our ODE, because those states are the input to our neural network, and also the neural network output. With those two data sets, so visualized here in the figure, with those two data sets, we can now build a regression problem where we want to identify possible candidate terms, theta, which enable us to recover whatever the NN is doing. And using PySyndy, we can build a library of those candidate terms, polynomials in our case, as given here in the figure as example. And then we use the PySyndy algorithm to obtain weights, which will tell us the importance of each candidate term. And from that, we can construct an approximation function, fnn, which, well, approximates the neural network. We can do so, and once done, we obtain an extended ODE. So we take the approximation, fnn, and insert it into our ODE, yielding a now fully analytical ODE again, which however is now extended by some additional terms. And in that example here, the additional terms that we need to improve our, well, flame model are kappa x2 and lambda x2 cubic. With those two terms only, we obtain now the purple response. And if you compare it to what we obtain in blue, so what we obtain with the UDE, meaning ODE plus NN, the response is very similar. It is significantly richer in its harmonic contributions, and therefore the output is significantly more nonlinear. This becomes especially evident when we compare the output to harmonic forcing of our extended ODE with the output of our baseline ODE, so where we all started from. And you can see that the extended ODE has now a strongly improved harmonic response. So we've demonstrated that using a UDE significantly enhances model capabilities, but we are still stuck with a neural network. So we went via PySyndy to our extended ODE, which also shows a strongly improved harmonic response. Remaining work now is, we now need to assign a physical meaning to the states of the model. So far we know what they mean in terms of oscillator states, but we want to understand what they mean in terms of flame dynamic states. So what does x.1, for example, mean in terms of flame and not in terms of dynamical system, which can be represented as an oscillator? Once we have this physical meaning, we can interpret the new terms that we learned from data only. And much further down the road, we would like to include additional very nonlinear effects, such as pinching, flame pinching, into our ODE model, something which by construction cannot be, well, captured so far. And with that, I'm at the end of this, presentation or talk, and I would like to thank you very much for tuning in. If you would like to have more information, you can either scan the QR code, which will lead you to our project page, or you find more information in the video's description down below. Here are the references of this talk, and, well, thank you so much, and goodbye.